This is section 8.1, day 1, and we're looking at sequences. A sequence is a function whose domain is the set of positive integers. So in other words, you plug in 1, then 2, then 3, then 4, and 5, and so on. So the set of positive integers. A sub n is called the nth term, and we denote the sequence by using these curly brackets. Write the first 5 terms of the sequence. So we're going to plug 1 in, then 2 in, then 3 in, then 4 in, then so on. So it ends up being the powers of 3. Here we're going to plug 1 in, 2 in, 3 in, just like we did before, except we're doing n factorial. Now keep in mind that 0 factorial is 1, 1 factorial is 1, 2 factorial is 2, 3 factorial is, 1 times 2 times 3. That's, not 3, but 6 rather. 4 factorial, we're going to take that 6, 1, 2, 3, and 4. So we'll take that times 4, that's 24. 5 factorial, 24 times 5 is 120. And it's nice to know 6 factorial as well, which is 720. Now, usually if we go past 6 factorial, we're looking at using some calculators. So if we go plug 1 in, you get 2. 2 in, you get 1. 2 over 2 is 1. 2 over 6 is 1/3. You get 2 over 24. 2 over 120, and so on. I guess not so on, but that's the 5th term. Arithmetic sequence. Each term is found by adding to the previous term. So in other words, adding is arithmetic. The value added is called the common difference. The explicit formula is a sub n equals a sub 1 plus n minus 1 times d. Now, if we wrote it like this, a sub n minus a sub 1, in other words, we subtracted over the a sub 1, and that's d times n minus 1, well, that's, like y minus 2 equals 4 times x plus 3. That's the point slope formula for a line. So really this is it's just a line. Geometric sequence. Each term is found by multiplying to the previous term. The value multiplied is called the common ratio. The explicit form is a sub 1 r to the n minus 1. So we're going to write an expression for the nth term on this. Well, we're adding 5 every time. So there's adding 5. 5 is really the slope. And we have a sub 1 plus d times n minus 1. Distribute the 5 through. That's 5n minus 5. I should probably use a different color. And so 3 minus 5, there's your negative 2. But that's not really how I would do it. I would say, well, the slope is 5, so we have 5n. Now, if I plug 1 into this, I get 5. How can I plug 1 in and get 3? Well, I would subtract 2 from this. Here we're multiplying r is negative 3. So we're multiplying by negative 3 every time. So a sub 1, r to the n minus 1. These are the perfect squares here, 1, 4, 9, 16, 25. And in letter D, these are one more than the power of 3. So 3 plus 1 is 4, 9 plus 1 is 10, 3 to the third is 27, plus 1 is 28, and so on. Sequences can be graphed on any graphing calculator by using parametric mode. So let's graph these. Let me grab the calculator. Can I slide this over? Hey, what's new in Chrome? Chrome must have updated. Come on. Oh, I had it. Clear. Let's go to mode. Let's go to parametric mode. So we're going to go down to parametric. And we get y equals, let me clear these. We're going to put t in for x, and then the function is going to go into y. So we have t divided by t plus 1. Whoops, I missed the divided by. Let's go insert and divided by. All right, well, now let's look at the window. We're going to go from 1 to 20. 1 to 20, and that's over here. We're following this over here. The step, instead of pi divided by 24, that's set up for trig. We're going to go by ones because we're plugging in 1 and then 2 and then 3 and then 4. And remember, it's the set of all integers, all positive integers. So now we have negative 1 to 20. And the y is negative 1 to 5. So we graph this, and we want dotted. We don't want it to be solid. So we're going to go to mode. Instead of connecting the dots when we plot them, we just want the dots. So when we graph, now we have the dots there. Now let's do the same thing in sequence mode. So we're going to go to sequence. And we're going to put the function into u of n, which for us is n divided by n plus 1. Now let's take a look at our window. N min is 1, so we're going from 1 to 20. We're going to start at 1, and our steps are 1. And then the x and the y should be set up from the last time, from the previous window. So when we graph it, we should get the exact same thing. Lab on investigating sequence. Let A be a sequence of real numbers. Now the terms, they can either go to infinity, go to negative infinity, they can converge to a value, or they can diverge by oscillation. So on number 1, here we have the graph, and we see that if we take the limit as n approaches infinity of n over n plus 1, that's just equal to 1. 1 over 1 when the powers are the same. Here when we take the limit, we're going to 0 because the denominator is going to go to infinity, and that fraction will be headed towards 0. Now here's the one that's a little different. Number 3. If we plug 1 in, we get 2. 3 minus 1. When we plug 2 in, that'll be 1. 3 plus 1 is 4, and then it goes 2 when we plug 3 in, and then 4, and then 2, and then 4. This diverges by oscillation, because you cannot converge to two different values. It's going 2, 4, 2, 4, 2, 4, 2, 4, and that is, we say that's diverging. So the terms are diverging. They're not converging to one single value. Number 4 is ending value again, ending behavior, so negative 1/2. This one, n wins the race to infinity. So here's your winner right there. So this is headed to 0. So I never said the answer on this. Converges to 0 on that one. N factorial. If you compare 20 factorial to 22 factorial, 22 factorial is actually much bigger. So if we can go 22, and factorial is in probability. So we're going to go 22 factorial, and let's compare that to 20 factorial. Those are both very big numbers, but 3 more decimal places is massively bigger. So n plus 2 is the winner on the race to infinity. So this one is going to converge. This converges to 0. The terms are converging to 0, and we can see that it converges to 0 rather quickly. Here the top is the winner to infinity. So this diverges, and we can see the terms are heading off to infinity. This one is oscillation, but if you look at the first few terms, 0, 1.5, 2/3, 5/4, 4/5, we have 0, 1.5, 2/3, 5/4, 4/5. 1 is right down the middle of that. So this is actually converging to 1. The fact that it goes below 1 and then above 1 and then below 1 and above 1, the distance between the values is getting closer and closer to 1 as we go. Now on this one, you go 0, 1/2, and we're going to look at this right here. If you plug in 1, you get 0, 2, you get 1/2, 3, you get negative 2/3, and it's going 0, and then it goes positive, negative, positive, negative, but the distance from 0, the distance from right down the middle, the numbers are getting farther away from 0. So this isn't converging to one single value. So this is diverging, I guess, by oscillation, but it just diverges because the amplitude to 0 is getting bigger and bigger. Now, if we look at this one, if we take, let's do this. Let's go 1 plus 1 divided by 10,000. And we raise that to 10,000. I didn't do that right. Let's try it again. 1 plus 1 divided by 10,000. 1, 2, 3. And we raise it to 10, 1, 2, 3. We're getting closer and closer to 2.718, which is E. Now this is 1 plus 0 is 1. If we put infinity in, that's 0. If we put infinity in for this, that's 1 to infinity. This is an indeterminate form. So we could, take the natural log, and once we take we can set the function equal to this, take the natural log, bring the n down, and do L'Hopital's rule because that's an indeterminate form. But once we throw that natural log in, the answer is going to be a power of E. And in this case, it's going to be e to the first. Well, we were really supposed to do that just with the graphs. We're supposed to investigate the graphs and see what's going on. So this one's really the limits. So the limit is 1 on this one, limit's 0. This one diverges by oscillation because we can see it goes 2, 4, 2, 4, 2, 4. This is the one that was negative 1/2 because we're really looking at ending behavior of a rational function. This one, n, is winning the race to infinity. I don't know why I have infinity here. This is 0. So this one, that is wrong, converges to 0. N's winning the race. So the bottom's winning the race. Here, the bottom is winning the race. So we're converging to 0. Here, the top wins the race. So now we're diverging. These terms are headed off to infinity. If we have the sequence 2, 4, 6, 8, 10, the series is 2 plus 4 plus 6 plus 8 plus 10. So find the first 4 terms of the recursively defined sequence, 4, 9, 14, and 19, because it's saying take the previous value and add 5. So we add 4, 5 to 4 is 9, add another 5, add another 5. There's the first 4 terms. Answer the following. 8, 4, 2, 1. R is equal to 1/2, and we see that over here actually. The 9th term, well, we have a half, a fourth, an eighth, a 16th, and a 1/32. So there's your 9th term. A recursive rule, the first term is 1/2. You have to say on recursive, you have to say where the sequence is starting. And then you take, to find the one you're on, if you want the third term, you take the second term and multiply by 1/2. So that's the recursion there. An explicit rule is a sub 1, r to the n minus 1. So the first term, a sub 1, is 8, and what we're multiplying by is 1/2. Now here's an example of kind of the foundation of the chapter. This is, and I wrote on the board in class, I'm doing this after class. This is a big deal. This is a big concept right here. Not necessarily cutting a cake in half, but what it represents. The limit of sequence versus limit of the series. So if you serve half a cake, and then you serve half of what's remaining, and then serve half of what's remaining, and half of what's remaining, and half of what's remaining, you could, in theory, you could do that forever. Now, you'd end up with some microscopic pieces of cake, but in theory, you could serve cake forever. Now, the terms are headed to 0. 1/2, 1/4, 1/8, 1/16, 1/32. The terms are headed to 0. The series, the sum, is actually headed to 1. So this converges to 1 cake. You can serve cake forever, but you're only going to serve 1 cake. Now, in order for the series to converge, in order for this sum to converge to a value, these terms must be headed to 0. If you're adding either the same, like 2 plus 2 plus 2 plus 2, that's headed off to infinity, or 1 plus 2 plus 3 plus 4 plus 5, the terms are headed to infinity. Well, the sum certainly is going to be headed to infinity. So in order for the series to converge to a value, the terms must be decreasing. They must be heading towards 0. So that's the whole point of this right here, and that's kind of the underlying concept of the chapter. Does the series for 5n have any chance of converging? In other words, 5 plus 10 plus 15 plus 20 plus 25 plus, no, that the terms are headed to infinity. The series is certainly headed to infinity, so no way. This has no chance of converging whatsoever. And that's kind of what I wrote down here. Now, what about the series 1 over n? Well, the terms are going 1 plus 1/2 plus 1/3 plus 1/4. So the series has a chance to converge because the terms are decreasing. The terms are headed to 0. So the series has a chance to converge to a value. But in this particular case, 1 over n actually diverges for the series, even though the terms are headed to 0. Exercise 1 through 4, find the first 6 terms in the 50th term of the sequence. So we're going to plug in 1, 2, 3, 4, and 5. And so the 50th is 2 and 49 50ths. Sketch a graph of the sequence. We plug in 1, 1, 2, 3, 4, 5 maybe, and we see those values and we plot them. Determine the convergence or divergence of the sequence with the given nth term. If the sequence converges, find its limit. So this converges to 2, because the limit, as n approaches infinity of this rational function that's ending behavior, the powers are the same. Now I use L'Hopital's to do this, but we know about ending behavior. Here, the power on the bottom is bigger, so it's like little infinity over big infinity. This converges to 0. This one is going, it is oscillating, but it's going negative 2/3, 1/2, negative 4/11. So that means it's getting closer. The amplitude is getting closer and closer to 0, even though it goes negative, positive, negative, positive. So this one converges to 0. The way you say this number is 9/10. So 9/10 to the n, right? So 9 to the n over 10 to the n. Well, now this is the winner to infinity. So this fraction, as the limit as n approaches infinity, is going to 0. If you plug 1 in, you get cosine of pi over 2, that's 0. 2 in, the 2's cancel. Cosine of pi is negative 1. 3 pi over 2, cosine of 3 pi over 2 is 0. 4 pi over 2, that's 2 pi. Cosine of 2 pi is 1. Well, now the values are just going to repeat. So we're going 0, negative 1, 0, 1, 0, negative. So this is not converging to a value. This is, this is really the cosine wave. So this one is diverging.